I'll stay here. Hi, my name is Bruno Ribeiro. I'm an assistant professor at the Computer Science Department. And I'm going to talk about representation learning, especially for logical formula. So one question that you might ask yourself is, are we close to the artificial general intelligence, right? Are we close to the singularity? And what I'm going to tell you today will make you a bit skeptical, I think. So this is how I see it, how deep learning really works, right? We have the training data, and we have a deep neural network. And so give some training data to the network. And it's trying to learn, right, some rules about the data, and it's paying attention. And now it's ready to execute. Notice that the girl and the little boy are different, right? They are not the same. They don't have the same type of body. So he is now confident. Okay, so what happens here is that deep neural networks essentially really learn to interpolate the data, okay? When you have it, they don't have any kind of intrinsic rule reasoning, okay? So there's no reasoning inside, it's just mimicking what it sees. And if the things seem a bit different between the training and the test, then things, as you see, don't quite work out. But then another question is, okay, so it interpolates, but is it a really good interpolator, right, for any kind of data? And we know all these tasks, right, that deep learning really excels: image, video, text, speech. So what do all these tasks have in common? Can you tell me? What is common to all these tasks? Using our eyes? Yeah, sure. So what they really have in common is that they all have some kind of canonical orientation. Okay, so you can basically make these inputs into vector or matrix, or basically like a vector. It's an ordered set, images up, down, left, right, text is left to right, and sound past to future. So neural networks are very good at learning things that have specific orientations. And that's because the basic building blocks of deep learning are these learnable functions of ordered inputs, okay? And there are basic 4 building blocks. The first 3 are things that we learn: feed-forward layer, convolutional layer, and recurrent layer. These are all sensitive to input orderings. Okay, so if you give a different input, it gets a different output. And there is one layer that is insensitive, which is deterministic. You don't learn it, you just average. It's a sum over the inputs, or a max, or a mean, or some average, okay? So that is not learnable, it's just fixed function, deterministic. So but the learning really happens at things that are sensitive to ordering. So here is a deeper challenge that I'm interested in, is how do you learn then with these invariances, right? Things that should not be sensitive to ordering. And I'm going to present 4 types of invariances, but I'll focus just on one of them. The first invariance is input invariances. You have here some Boolean formula. You can see that you give this formula to a neural network. You expect to get the same output no matter how you present the formula, right? Because these variables are exchangeable inside the clauses, and the clauses themselves are exchangeable. Like you can just permute them, and it's the same formula, and it doesn't change. But if you think about ordered inputs, they are very different, but they mean the same thing. So the first question is, how can we learn functions that if you give any ordering, you get always the same output? Okay? So that's for input invariances. Their output invariances say that you read the Lord of the Rings and you see what the characters are doing in the book, right? And then you try to come up with some reasoning about how humans behave, right? Because the author is human, probably built in some rules of behavior. For instance, the enemy of your enemy is your friend, for instance, right? You can try to learn that from the book. So here, the invariance needs to be to the output. So the model will output something that needs to be invariant, right? All these logical rules have some invariances in them. So this for output invariances. Surprisingly, output invariance is a harder task still. We don't quite know how to do it well than input invariances. Input invariances, we made a lot more progress than output invariances. Another type of invariance that Pushmit just talked about is invariance to noise, right? You want a function to not be sensitive to a little bit of noise, which gives you a notion of robustness. And in the case earlier that I was showing is really a fourth type of invariance, which is domain invariance. So we have some training domain. The girl is taller, heavier, and more flexible. The boy is shorter, lighter, and more rigid, right? So once learning from the data of the girl, how can the boy then execute, right? So that requires not just to interpolate, it must learn rules that are invariant across these domains, okay? There are some very interesting reads on how invariances are related to this idea of extrapolating from training data. So today, what I'm going to talk about, I'll just focus on type 1, which is input invariances. And progress generally in science forces us to turn back the clock. And so one interesting, important thing about invariances is that they look very simple on the surface, but actually they have incredible deep implications. So when Einstein was not sure what relativity meant in terms of conservation of energy, he enrolled Emily Noether, who proved that if your experiment has some type of invariance, it would imply some law of conservation. For instance, if you make an experiment that doesn't matter when you start and where you started, then it must conserve energy. And because you have relative time, there is no energy conservation. And that was 1918. So she basically predicted dark energy. Okay, so this is just the fact that your experiment is invariant means something very profound. And we find this also for statistical machine learning. So here are some types of invariances. And this is a bit technical, I apologize. But so when we define a joint probability distribution, which is a probability over a sequence of variables, x1 to xn, x can be some space very abstractly. Then to define this joint distribution, something that you must have learned in Stats 101. For instance, the sequence here, the sentence, first variable is the first word, second variable is the second word, the ninth variable is the last word. Okay, so in this sequence example, we have a probability over the sentence. So abstractly, if we can think of a joint probability just as a function that takes high dimensional input and ordered, right, and outputs some value between 0 and 1. It needs to be normalized, but that doesn't really matter. It's just a function that takes an ordered input and outputs a value, okay? Now, what should I do if I'm trying to define a probability over a set? I have a set of variables and the order doesn't matter. But remember that probability distributions are defined as ordered sequences, right? Then what should I have here? I need another property of this probability. And the property is that the probability is the same no matter which order I give you, okay? It's invariant permutations of the input ordering. Does that make sense? Yes? In point processes, these are known as Janus densities. So there are some really interesting work to read that I recommend on this. But so if we are trying to look at invariances and input invariances, the first one is really on sets, right? So what's the progress on sets and multi-set invariances? So we have some logical statements or some set of points, and we want to learn a function that maps that into some decision we want to make. So there is a growing interest in neural network architectures that are set invariant, right, for set inputs. And one interesting thing is that we recently realized that there was a generalization over all these methods, that they can be generalized into one single framework. And that single framework is basically a learnable function that doesn't depend on input orderings. So now we basically have neural network layers that are invariant to input permutations, okay? So we have a good idea how to deal with those. Although sometimes they can be expensive to learn, but we know how to deal with them. So what about graphs, right? Graphs is another type. We talked about sets. Let's talk about graphs. And graphs are very connected to logical formula because we have here the clauses, okay, and we have the variables. The dark edges mean that the variable appears in the clause as positive, and the red means that appears as negative. So I can represent that formula exactly through this bipartite graph, okay? So now the question is, if I want to represent something about this formula, I need to learn how to represent this bipartite graph. So here's a problem with representing graphs. We represent them as adjacency matrices. So we have zeros where there are no edges and 1 where there are edges. But when we create this adjacency matrix, we need to say this is the first node, this is the second node, this is the third node, this is the fourth node. So we need to give them IDs to be able to build the matrix. So we use arbitrary IDs. So clearly, then, whatever function or that I'm learning over this matrix, over this graph, needs to be invariant to whatever random choice of IDs I had, right? It needs to basically give the same answer to any decision that I made to label the node IDs. But so it sounds easy enough, but it's not that easy. For instance, there's two graphs here, right? We have two fake molecules, okay? Forget the numbers and the letters, just look at the colors. Is this the same input? Or are they different inputs? Same? Same? Someone said same? Huh? It's scrambled, right. So they are actually the same graph, okay? But you can see that it's not trivial to decide that. So this is actually known as a graph isomorphism problem. So you decide if two graphs are isomorphic. It's a quite hard problem. So how should we represent a graph input to a neural network then, right, if this is a difficult problem? So the first property, as I said, is that the input must be invariant to permutation. So if I decide to relabel the nodes with this permutation pi, and I give a new adjacency matrix, whatever my neural network outputs needs to be the same, no matter which permutation pi I give, okay? So whatever random node IDs I give. So how to guarantee invariance to node IDs? So let's make a quick detour into graph isomorphism tests, right? Let's get some ideas here. It's a very old problem, so we should be able to get some interesting insights. So there is this Weisfeller-Lehmann algorithm or color refinement algorithm that some of you may know from your algorithms class. It's a recursive algorithm that to determine if two graphs are isomorphic. The algorithm is actually extremely simple. It's a valid isomorphism test for graphs. And it's extremely simple. You just do a certain number of times until it converges. You loop through all the vertices, and then the color of a given node is the color of itself in the previous step and the color of the neighbors, a hash between your color and the color of the neighbors, and that's it. And you run this until it converges. Sometimes it converges, sometimes it doesn't converge, but if it converges, you're guaranteed that if these two graphs are isomorphic, they'll have the same set of colors, okay? The problem is that there are some graphs that are not isomorphic that you can't distinguish. how can we bring back to neural networks, right, this idea? So what graph neural networks, who here has heard of graph neural networks? Some people. So if you had never heard of graph neural networks, I'm going to tell you what graph neural networks are in 5 seconds. Okay, ready? So graph neural networks are exactly the Weisfeld-Lehmann test algorithm, exactly, where we replace the hash function, exact same algorithm. We replace the hash function with a neural network, and that's it. There's nothing else. It's exactly the same algorithm, okay? In the end, at the end of the algorithm, we can't wait until it converges, so we say that we are going to apply k iterations, which are here k layers. And in the end, we get a representation for node V. And that representation, because the algorithm is an isomorphism test algorithm, is guaranteed to be invariant to these permutations, the random permutations of node IDs that I initially gave. So this actually recently was shown to be as powerful as a Weisfeld-Lehmann test to recognize if two graphs are isomorphic, okay? So it basically means that it's a very good test for like it can really capture structural information from the graph. So by construction, they are what we call permutation equivariant, which means that if I say that node ID, this is node ID 1, then the first representation for a node is going to be the one that I said it was 1. The second one is going to be the second one that I said, that I gave IDs 2. It will be the second representation. So it's a type of invariance, but if you permute things, you're going to expect the nodes to shuffle also. So what we show, of course, is that these GNN representations can fail, and we created a task where they provably fail. So there is no GNN method, existing GNN method that can succeed on this task provably, because the Weisfeld-Lehmann test fails on the same task. So they can't work. And then we have a solution for that, but I'm not going to bother you with the solution. But what's another interesting thing that's related to learning logic is that these graph neural networks will fail as what we consider very simple tasks. We are trying to predict relationships, and they essentially cannot predict relationships. They are not designed for that. So here we have a food web, right, between the land animals and sea animals, and they are disconnected, okay? So they say they don't eat each other. So if you run a GNN over this entire graph, which is disconnected, you are going to get a representation of the nodes. And this representation is unrelated to closeness. No matter what your neural network parameters are, it will never give you a notion of closeness. It will give you a notion of structural equality. If two things are structurally similar, never closeness. So, for instance, we can prove that the output of any GNN over this graph, the links, the representation that you get for the links and the orca will be exactly the same. So now you want to predict with those representations whether the lynx eats the coyote, then the orca should also eat the coyote. Okay? Which is a very scary world, right? Could be, but it would be a very scary world. So this essentially failed. If you think about using GNNs for representing logical formula, usually you're talking about relationships, and this will fundamentally fail to predict relationships. Okay, so GNNs are not good for this task. At least not in their traditional way that they are designed. And if you are itching for some theory, there is also a probabilistic definition of these probabilities that are invariant over permutations of the indices. So I just have some random variables that are defined over two indices, and if I say that the indices need to be, the probability needs to be invariant to permutations, it means that this is really like a graph model. So we recently, we can prove actually that all GNNs output node representation must fail in the use of these relationships. And really, the tool that we have today to predict relationships is this tools of node embeddings, which define some distance, and then you create an embedding. You try to learn vectors. You try to learn a projection in some other vector space that kind of match the distances that you see in the graph. And this is a low distortion embedding, really is what preserves distances, but this is kind of incompatible with our use of neural networks, so it's hard to do that. Okay. So there is some long history on this, but what we now understand is that the idea of node embeddings and graph representation we always thought to be different actually have a unifying theory. We now understand them as something having a deep relationship. So node embeddings and graph representations are what samples are to distributions. So we show how to create graph representations for relationships, so that can be used for logical formula, and we show how to get representations from node embeddings and vice versa. So basically, what were two separate worlds now have been connected. And so the take home here is really that it's going to change the way we do machine learning, I think, because of input invariances, input representations, output representations, robustness, learn models that can learn rules of formula and program synthesis. Without invariant theory, I think we are going to be a bit stuck in our progress. And with that, thank you for your time.
All right.